All right, so that would be the graph of 2 plus 2 sine theta. So make sure you put your calculator in polar form. So this is no longer an x and y axis. It's a pole with, circle radiuses, and then, this is the polar axis, and this is the theta equals pi over 2 axis. So you type in 2 plus 2 sine theta, and that's what it looks like. All right, then if we change it from, we keep it sine, but we go 2 minus 2, it looks like that. Then if we go back to plus and change it to cosine, looks like that. And if we make this negative, it looks like that. So does anyone notice any patterns here between any of these coefficients or when we change sine and cosine? So what do you notice about if it's 2 plus or minus 2 cosine? So there's 2 minus 2 cosine. Here's 2 plus 2 cosine. Yes? Yeah, and I would say more reflects, because shift would imply it's in the same direction. But where's the symmetry when it's cosine? Over what axis does it have symmetry if it's a number plus or minus the same number times cosine? Yeah. Yeah, the horizontal axis. It's symmetric. So I know what you're saying. So you're right. If I were to change this from minus to plus, it reflects over the y-axis. You're 100% right. But what line of symmetry do both of these cardioids have? If it's cosine, it's going to be symmetric over the x-axis, right? And I think of it as cosine is x over r, so it has symmetry over the x-axis. Or cosine is before sine in the alphabet, x is before y in the alphabet. So cosine is going to have symmetry over the x-axis, and sine will have symmetry over the y-axis. So if it's negative, it'll be the bigger part will be in the negative direction, so to the left or down. And if it's positive, it'll be in the positive direction. All right, up or to the right. Now, what do we think? Do we notice any connection between the two and all these graphs? So notice how it crosses the axis at 2. So we got 2 special points that are 2 units away from the pole, and another special point. By special, I mean it has a nice integer. This would be 2 comma 0, and this would be 4 comma pi over 2, and this would be 2 comma pi. All right, so special, I mean it has integer length radiuses. So the 2 will tell us where 2 of our special points are, how far away they are from the pole. So if I change this to 3 plus 3 sine theta, now those special points would be 3 units away from the pole, and the other ones would be 6. Now, just for fun, let's say we made these numbers different, a 3 and a 4. Now it's no longer a cardioid. It's got this little loop over there, and that's pretty cool, but it's not something that we're going to graph. So cardioids for us will always be in the form where it's a plus or minus a times sine. All right. So let's summarize that. And we're gonna graph these directly, where everything we just talked about, theoretically, you don't need to know, but it definitely helps if you know those things so that you could check your work, and sometimes you could graph it without having to graph it in rectangular form. So what does sine cosine tell us about the graph? Well, if it's sine, remember sine is y over r. Sine will be symmetric over the y-axis. And really, that's not called the y-axis. That's really theta equals pi over 2. But, I mean, we all know it's the y-axis. And then cosine is symmetric over the x-axis. All right, which is really the polar axis, which is where theta equals 0. All right. And for some reason, my camera is really zoomed in today, and I don't know how to control it. So if you can't see what I'm writing, just tell me. Oh, there we go. I just zoomed it out. All right, and then the plus and minuses, what does that tell us about the graph? If it's a plus, what was that? Oh my God. All right, we're okay. All right, so if it's positive, if it's 2 plus sine, 2 sine, or 2 plus 2 cosine, the big part is in the positive direction. And then if it's negative, then the big part, there may be a mathematical term for that. I'm not quite sure. I'm going to call it the big part. The big part is in the negative direction. All right, all cardioids have a dimple in the direction they face, 5 key points, one of which repeats. So let's graph one using our knowledge of, y equals 3 plus 3 sine of x, and also the knowledge that we just learned by like the patterns that we saw. All right. So first, we're going to graph the rectangular function, which means don't graph it on a polar axis, graph it on an x and y axis, but our independent variable is theta, so that'll be like our x, and our dependent variable, like our y, is going to be r. So this would be a sine curve shifted up 3 with the amplitude of 3. So since it's shifted up 3, it's going to have like a middle axis at y equals 3 or r equals 3, and then a maximum at 6 and a minimum at 0. And we'll graph just one period. If we need to graph more, we will. But I already did this, and no, we don't. So we'll sneak peek. All right, and then we'll mark off our increment. So that's half of a period, that's a quarter of a period, and then pi over 2, 2 pi over 2, 3 pi over 2, that'd be 3/4 of a period. So we got all 4 quarters, we got 4 increments there of one period. All right, so sine starts on the sinusoidal axis, it starts in the middle. So we'll always start there. And then if it's a positive amplitude, it's going to go up. If it's a negative amplitude, it's going to go down. No problem. We got, these are too big because they're blocking the fire exit. That's what I was told. I'll trade you 2 big boys for 2 little boys.
Is on this side you don't get them.
Yeah, that'd be perfect.
All right, I'm going to get them now.
Thank you very much. Thank you.
All right, sir.
Appreciate it. All right, so bang, and we're back to the sinusoidal axis. We're back here, and then back to there. Now, those 5 points, we're going to graph all 5 of them, even though 2 of them are like coterminal, they're going to repeat. But we should also connect the dots because we're interested in like where the radius is increasing and where it's decreasing. And I'll explain why. All right, so now we got to graph our polar points. So this is the point 3 comma theta equals 0. So we'll start on 0 and then go 1, 2, 3 right there. And then the next point would be at 6 comma pi over 2. So pi over 2 is right here, and we'll walk out 6. 1, 2, 3, 4, 5, 6. All right. Now, I think it's also a great idea to graph points where like sine of an angle or cosine of an angle will equal 1/2, because those would be like really easy points to graph, because like we could do 1/2 times 3. So what do I mean by that? Like in between these 2 points, so we could like trace out our curve a little more accurately. Let's also evaluate like pi over 2. So like when theta is pi over 6, because that's 30 degrees. And we know that the sine of 30 degrees is 1/2. So if we plugged in pi over 6, it'd be 3 plus 3 times 1/2. So 3 plus 1.5 is 4.5. So we got pi over 6, and then that's 4.5 right there. All right, so now I want you to like imagine that like this angle, my pen is like representing the angle, like as it's rotating from 0 to 90 degrees, just like here, as it goes from 0 to 90 degrees, R is increasing. So as you rotate from 0 to 90 degrees, these points should be getting farther and farther away from the pole because R is increasing. So that's where that like big part comes from. All right, and then now if you've graphed these a couple times and you think about like what it looked like on our calculator, since it's sine, it's going to have symmetry over the y-axis. So like that means there'll be another point here at 4.5 comma 5 pi over 6. And then at 3 comma pi. So you can use that symmetry or just use the graph. Like, all right, we got pi comma 3 is right here. And then another angle where the sine of that angle is 1/2 would be 7 pi over 6, which is 4.5. All right, so then now as you go from pi over 2 to pi, R is decreasing. All right. And I mean, if you want to get really accurate, it can't hurt to also graph the other 2 points where theta makes sine of theta negative 1/2. And I wrote 7 pi over 6 because I'm an idiot. I meant to write 5 pi over 6. But I'm not an idiot. I'm just overzealous. I'm thinking about the next thing. So maybe just zealous. Maybe not overzealous, just the right amount of zealous. Overzealous is kind of like redundant. Doesn't zealous kind of mean overzealous? I don't know. Someone look that up. All right. So 7 pi over 6. All right. So the sine of 7 pi over 6 would be negative 1/2 times 3 is negative 1.5 plus 3 is 1.5. So you have another point right here at 7 pi over 6 comma 1.5. And then as we go from pi to 3 pi over 2, so like this angle to that angle, R is decreasing to 0. So like as you're rotating, you're getting closer to the pole. And that's where that dimple occurs. And then from 3 pi over 2 to 2 pi, it's going to be like increasing to 3. And on the way, it's going to hit 11 pi over 6, which we can all evaluate if we remember our trig stuff from earlier in the year. The sine of 11 pi over 6 is negative 1/2 because it's a 30-degree reference angle in quadrant 4, times 3 is negative 1.5 plus 3 is 1.5. So we got 11 pi over 6 comma 1.5. And then as this rotates, we create that other dimple there. And that's our first cardioid that you ever graphed. You always remember this moment.
Yeah, you were right about overzealous.
It's the same thing, right?
Yeah, well, no.
No.
Overzealous is too much zeal.
Too much zeal. But what is zeal? Isn't zeal implying that you're like giving too much effort in the first place?
Yeah, like overzealous.
Oh my God.
Too zealous, too enthusiastic.
So I think I was just zealous there.
Yeah.
Yeah. Just like medium zealous. All right. Thank you for confirming that. I listen to too many podcasts. So sometimes I think I have my own producer. I'm like, Jamie, look that up. And then, all right, nice. Let's do another one. But basically, these aren't too bad. You just, plot these 5 points and you kind of know what the shape looks like. And yeah, so let's do it. Let's do the next one. 4 minus 4 cosine theta. So, it said identify the values of theta for which one full curve is traced out. So that was just from 0 to 2 pi. All right. Now for this one. All right, this would be the theta axis and this is the R axis. All right, we're going to graph 1 period, 2 pi. All right, half a period is pi. Half of that is pi over 2. And then 1, 2, 3. That'd be 3 pi over 2. So we got our increments. And it's always good to simplify these because they're simplified on the polar curve. All right, so we're going to have a maximum of 8 because this is shifted up 4. So the midline, the sinusoidal axis is at 4. and it has an amplitude of 4. So like the max would be 8 and the min would be 0. So cosine always starts at the max or the min. And since there's a negative in front of the amplitude, it's going to get reflected. So like Drake, this will start at the bottom. All right, and now we're here. And now the whole team's here. And we're back down here. And back to there. All right. And connect the dots. All right, so yeah, and the curve is important because it shows us like, all right, where are we getting farther away from the pole and where are we getting closer to the pole? So, and this is why cosine ones are going to be like symmetric over the x-axis, because cosine always starts at the max or the min. So like the big part or the dimple is always going to be like on the x-axis on either side. All right, so we're going to start at 0 theta, 0 r. So that's right here, right in the pole. And then for pi over 2, we're going to be at 4. So 1, 2, 3, 4. Now, to connect these dots, like as you rotate from here to here, it's getting bigger. So if we want to get a nice accurate curve, we can graph one more point. And I suggest doing theta or pi over 3, because the cosine of pi over 3 is 1/2. So 4 minus 4 times 1/2 is 4 minus 2, which is 2. So at pi over 3, we get 2. And now we could like hit all those points. And that's like half of our dimple side, which I believe is an actual mathematical term because it was in these notes, which I didn't make. It was shared with me. Shout out Miss McCullough. She's a real one. All right, pi 8. And shout out Miss Troncali too. She also helps me out with like some of these questions she provides. All right, so now we're at pi 8. So we're gonna go pi and then 1, 2, 3, 4, 5, 6, 7, 8. Oh, I should have went. That's fine. All right. So now we got to connect these. And as we connect them, it's going to be getting bigger because on this interval on the graph from pi over 2 to pi, r is getting bigger. So if we want to find one more point, we can use another one with a reference angle of 60. So 2 pi over 3. So the cosine of 2 pi over 3 would be negative 1/2. So negative 4 times negative 1/2 would be positive 2. So 4 plus 2 would be 6. All right, so now we're at 2 pi over 3 comma 6. 1, 2, 3, 4, 5, 6. So as we rotate from pi over 2 to pi, all right, we're getting bigger there. All right, and if you know that cosine is symmetric over the x-axis, then you could just reflect these points over the x-axis. And I use quote air quotations because it's really the polar axis. So like the other point would be here at 4 pi over 3 comma 6. And then here would be 3 pi over 2 comma 4. And then one more, which is like at 5 pi over 3 comma 2. All right, so that I was just using symmetry, but like you could have also found these points by like looking at our graph. So like 3 pi over 2 comma 4 is right there. And then these other two we just used, you know, I just evaluated because I know that the cosine of 60 or any angle with a 6-degree reference angle will be 1/2 or negative 1/2. So like this one would be 6 because we're in a negative cosine quadrant and a negative times negative is a positive. So that's 4 plus 2. And then here, like 5 pi over 3, that would be at 2. All right, so there's another cardioid. Yeah. Oh, I got a question on that. All right. Are these called cardioids because cardio means heart? Wow, that's a great call. Are these called cardioids because cardio means heart? And these look like graphs, look like hearts. That would make way more sense than Cardi B invented them. But yeah, I think you're right. I think it's because of hearts, because they do look like hearts. I mean, I'll address the elephant in the room. I think they look like butts, to be honest. But cardioids, I mean hearts, they look like hearts. Actually, if you're gonna go with like the playing cards reference, I think it looks more like a spade than a heart, to be honest. With you know, it's yeah.
Cardioid means Greek is, according to the internet, it's Greek for heart.
There you go. Thanks, Jamie, my producer, for looking that up. Appreciate it. Jamie's the producer on the Joe Rogan show. So I'm just calling him Jamie randomly. But that would make sense. Yeah. If I did any thought about this before, that maybe I would have thought of that. But thank you for pointing it out. That's why we cracked the code. It's not because of Cardi B. I could have swore it was Cardi B, but well, maybe Cardi B is named Cardi B because she's got a big heart. All right. Very nice. Yeah, that would make sense because they look like hearts. I wonder why they call these rose curves though. That was a joke because they kind of look like flowers and flowers are roses. Although they don't really look, I guess when a rose opens, I don't know. It looks more like other types of flowers, like clovers. All right. Great call, Isabel. Way to be thinking outside the box. All right, let's do one more. Well, let's finish this page. So r minus 8 sine theta. So let's graph that. All right, so this will have a sinusoidal axis at 8. The maximum is at 16. And that's 0. So this is our theta axis. This is our r axis. All right, so 2 pi, pi over 2, 3 pi over 2. All right, that's because the period for all these is just going to be 2 pi because there's nothing in front of theta. You know what? I wonder what happens if we put something in front of theta. I'm curious. Let's just see. This is, whoa, that's sick. Look at that. It's like an infinity. What? Hey, what? That's like a, I thought those were rose curves. Yeah. Whoa. All right. Wait, I bet there's going to be 6 petals. Yes. What was that? Yeah. All right. We'll do that another day. We'll do that in July if we're still here. We'll cover those. All right. So 8 minus 8 sine of theta. So that's going to start right the midline because it's sine. Because the amplitude is negative, it's going to go down. And then work its way back up. And back to the top. And right back to where we started. All right, so that's one full period. Connect the dots. All right, so now let's graph these. So there's only room for like 8 tick marks, and our biggest point is going to be 16. So let's not get too zealous. Definitely not overzealous, but let's make this 16 so that we know that like each tick mark is worth 2, or else we'll run out of room like a zealot. I think that's the noun. All right, so 0, 8 would be 2, 4, 6, 8 right there. And then pi over 2, 0 would be right here. So this is like there. And then as you rotate to 90, it's getting like closer to 0 because we're decreasing. So if we want to find like one more point to make sure that we hit it's the right orientation, we can plug in pi over 6. So basically you want to plug in like pi over 6's like 5 pi over 6, 7 pi over 6, 11 pi over 6, anytime it's sine. And anytime it's cosine, you could plug in like pi over 3, 2 pi over 3, 4 pi over 3, 5 pi over 3. All right, if you haven't noticed this, like if you simplify these, then like the pi over 6 part, disregarding the coefficient, is always like the reference angle. So like 60-degree reference or 30-degree reference angle, 45, 60, 90, 60, 45, 30, 30, 45, 60, 90. So like pi over 2, 3 pi over 2 tells me it's a 90-degree reference angle. All right, so that would be at 8 minus 4, which is 4. So right here, so that'd be 2 out. So like 2, 4 right there. All right, so this will be our dimple side, because as we're rotating from 0 to 90, we're getting closer to R. And then from pi over 2 to pi, it's going to extend out to 8. So that's 2, 4, 6, 8. And since it's sine, it's going to have a line of symmetry over this y-axis. So there'll be another point at 3 pi over 4, comma 4. So it'll look like that. And then from pi to 3 pi over 2, it's getting longer, all the way till we reach 16 comma 3 pi over 2, which will be 2, 4, 6, 8, 10, 12, 14, 16. All right, and then on the way, all right, we already hit 5 pi over 6 comma 4. Now 7 pi over 6. The sine of 7 pi over 6 would be -1/2. So -8 times -1/2 is +4. 8 plus 4 is 12. So 7 pi over 6 comma 12. All right. 2, 4, 6, 8, 10, 12. So it's extending and getting longer. All right. And then it's got the symmetry over the y-axis. So there'll be another point here. All right. 2, 4, 6, 8, 10, 12. Boom. Beautiful. All right, identify which values. Okay, we did that already. That would just be 0 to 2 pi. All right. Now let's try to work backwards. All right, write the equations of the curves below. So for that, you could just kind of like recognize this pattern and know that, all right, if it's in this form, like the farthest point will be at R equals 2a. So like for this one, like the farthest point was at 1, 2, 3, 4, 5, 6, because A was 3. And here the farthest point was 8, because A was 4. So you could look at this and be like, all right, that's 5, so that's probably 6 right there. Because, you know, if we equally space these out, that would make sense. 1, 2, 3, 4, 5, 6. So that means that's equal to 2a. So A would have to be 3. And since it's symmetric over the x-axis, it would be cosine. So it'd be R equals 3 blank 3 cosine theta. And then it would be positive because the big part is in the positive direction. So that's one way to do it, just by using like the patterns that we learned. All right, or the other way to do it, which you might find easier, would be to take the polar equation and then graph the rectangular one. So we'll do that for this example. All right, so if we look at the points here, it goes from like R equals 4 to R equals 2, R equals 2. So if this is the R axis, it goes from 0 to 4 with like a midline of 2. All right, and then so this, we'll say that's one full period. All right, so this starts at 0 degrees, comma 2. So theta is 0, r is 2. And then when you rotate from 0 to 90, r is decreasing until it hits 0. So it's going to go down until it hits 0. And then from pi over 2 to pi, it's increasing to 2. And then from pi to 3 pi over 2, it's increasing to 4. And then from 3 pi over 2 to 2 pi, it's decreasing back to 2. And then if you have this, and you remember how to write an equation of a graph or equation based off a graph, then you know, okay, this is shifted up 2. So like plus 2, and it's sine because it starts in the middle. So r equals sine theta, and it has an amplitude of 2, but it's going down, so it's reflected. So it'd be negative 2 sine theta plus 2. And then we usually, I don't know why I put the 2 so far over there, but like that's the same thing as writing like r equals 2 minus 2 sine theta. All right, so you can also do it that way. All right, any questions? All right, last thing, let's just practice finding the key points here, and then we'll cut this short. So, all right, so for the polar point, when theta equals 0, all right, we could plug in 0, and remember we put theta second, and then r first. So it's r comma theta. If you plug in 0 for theta, cosine of 0 is 1. So 9 plus 9 is 18. All right, we'll convert these after. Then if you put in pi over 2, the cosine of pi over 2 is 0. So 9 plus 9 times 0 is 9. All right, so you could kind of do this without the graph if you get good at this, but I think the graph always helps too. All right, if you plug in theta, if you plug in pi for theta, the cosine of pi is 0. So 9 plus 9 times 0 is just 9. Wait a minute, what am I talking about? The cosine of pi is -1. I apologize. So if we plug in pi, that's 9 plus 9 times -1, which would be 0. And then if we plug in 3 pi over 2, I'll be right with you, one sec. Then that would be 0. So 9 times 0 is 0, plus 9 would be 9. All right, so now just take a second and convert these to rectangular. So remember x equals r cosine theta, y equals r sine theta, and that's what we're using to convert these. And then I'll show you the answers in like 2 seconds. And I'm going to end this recording.